Welcome back to part 2 of solving these practice problems for integration. So as we left off, we're on number 9 now. Find all the antiderivatives of the following function. So we're looking for the antiderivatives. In other words, we're looking for the function who this right here is its derivative. Whose derivative is 4x cubed minus 3x squared minus 6x plus 2. So as you can see from the solutions, it would be x to the fourth minus x cubed minus 3x squared plus 2x. Don't forget this constant right here, this plus c, because remember, we're looking for the antiderivative, and the derivative of any constant is 0. So there are technically infinitely many solutions to this problem right here. We need to account for them all by adding this plus c. You can always check that your antiderivative is correct by taking its derivative. If you take the derivative of x to the fourth minus x cubed minus 3x squared plus 2x plus c, you do in fact get this 4x cubed minus 3x squared minus 6x plus 2. What's the antiderivative of e to the x plus 5? In other words, whose derivative is e to the x plus 5? Well, that's going to be e to the x plus 5x plus a constant c. And again, you can check by taking the derivative of this and making sure you get what we started with. Whose derivative is 1 over x? Well, we know that's the natural log of x. However, we have to remember that you can't take the natural log of a negative number, so we take the natural log of the absolute value of x, plus we need this c right here to account for all solutions, since there are infinitely many. Finding antiderivatives is incredibly similar, if not the same, to finding indefinite integrals. So if I wanted to find the indefinite integral x to the fourth minus 5x squared plus 12x minus 9 dx, that means with respect to x, I'm looking for whose derivative is x to the fourth minus 5x squared plus 12x minus 9. So using my antiderivative rules or my integration rules, I get x to the 4 plus 1 over 4 plus 1 minus 5 times x to the 2 plus 1 over 2 plus 1, that should be a 3, plus 12 times x to the 2 plus 1 over 2 plus 1, which will reduce to 6x squared, minus 9x plus c. So remember, that's supposed to be a 3 right there. That's my mistake. If I wanted to do the antiderivative of 3 over x cubed plus 2 over x squared minus 1 over x, now the first thing I would do is I would bring this x cubed up, and I would call that 3x to the negative 3. I would bring this x squared up, so I would call that 2x to the negative 2, but I would leave this as minus 1 over x, because if I brought the x up and gave it a negative exponent, it would be negative 1, and we can't use the power rule for negative 1. So then when I follow my integration rules there, here, again, it's 3x to the negative 3, so it'll be 3x to the negative 3 plus 1 over negative 3 plus 1, plus 2x to the negative 2 plus 1 over negative 2 plus 1, plus the natural log of the absolute value of x, plus c, and then we reduce our answer, get rid of negative exponents, and here's where we are. For c, very similarly, I'll rewrite this as a fraction exponent. And I'll rewrite this as a fraction exponent, but I'll bring it up and give it a negative exponent. And then I can follow my power rule, t to the 3/5 plus 1 over 3/5 plus 1, plus t to the negative half plus 1 over negative half plus 1, and then simplify. So that's what I did here. For d, 5e to the x minus ex to the e right here. Now remember, e is a real number. It's about 2.718281859. So this was x to the 2, we would say that would be the antiderivative would be x to the 2 plus 1 over 2 plus 1. But it's not, it's 2.7 blah, 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 which is why I considered that e to the plus 1 over e to the plus 1. The antiderivative of e to the x is e to the x. And again, you can always check that your antiderivative is correct by taking the derivative of what you get and making sure you get this integrand inside here. For e, here we have two things going on, right? We have y to the third minus 4y times 3y squared minus 8. So what I did is I actually just made my life easier and I FOILed this out. Everybody in the first group got multiplied to everybody in the second group, which gave me 3y to the fifth minus 8y cubed minus 12y cubed plus 32y. Combine my like terms, and this is something that's a lot easier to take the antiderivative of using our power rule and our sum and difference rule. And I get y to the 6th over 2 minus 5y to the 4th plus 16y plus c. Again, you can take the derivative of this and make sure you get this integrand right here that we started with. It's just when you take the integral or the derivative of this, you'll have to factor to make sure you get that integrand in the middle. Here, for f, we don't have a quotient rule. So what I suggest doing is dividing everything by x squared, right? Take the x6 divided by x squared, the 5x to the 4th divided by x squared, and the 7x divided by x squared, and the 1 over x squared. So that's what I did. I divided everything by the x squared and simplified. Keep in mind, when you have an x by itself with no exponent in the denominator, you can't bring it up and give it a negative exponent. It's not going to work, right? That would give you a 0 in the denominator. That's your natural log. Then I used my power rule and sum and difference rule to come up with this antiderivative here, which said that the definite integral of what I started with was x to the 5th over 5 minus 5x to the 3rd over 3 plus 7 times the natural log of the absolute value of x plus 1 over x, and of course, our constant of integration plus c. Now for g here, what we did up here for e is we kind of, what you call FOIL, we FOILed it out and simplified. The problem with that is this to the 3rd power right here. We would have to take x squared minus 5x times x squared minus 5x times x squared minus 5x and distribute that all the way out, and then distribute that 4x minus 20, and then combine all our like terms to solve it that way. That is something that's possible, but it's a lot of work, and I highly recommend you not doing that. So instead, we're going to use that trick that we talked about, U substitution. So one of the things that we said, if anything is being raised to a power or under a radical, we want to try to choose that as u. So we're going to choose this x squared minus 5x since it's being raised to the 3rd power and choose that as our u. So our u will be x squared minus 5x. So then our du would be 2x minus 5 dx. There should be a dx right here. Now notice that the 2x minus 5 dx doesn't match the 4x minus 20 dx. It's off by a factor of 4. That's a mistake. Well, I made a typo, as I can see now that I'm going through this. This problem doesn't actually work as nice as it should, so we're going to pretend like that is an 8x minus 20. That would make life a lot easier. So that should be a 4. That should still be a 2x minus 5, and that would work out really nice. Pull out the 4 like I did here if I had done my math correctly. Sorry for those of you that struggled with this problem. I'm just now realizing I made a mistake. Then this 2x minus 5 that it should be, dx would be equal to my du. This would be u to the 3rd power. I've got that constant of 4 I pulled out. So then I have 4 times the integral of u cubed du. That 4 carries through, u to the 3 plus 1 over 3 plus 1 plus that constant of integration. And of course, these 4's cancel, and we need to plug back in what u is. Sorry for that typo. All right, let's take a look at h. E to the 3q over 5 plus e to the 3q. So one of the things that we said, kind of our rule of thumb with u substitution, is we want to try. It's trial and error. We have a lot of work to do, right? It's not always going to be the same thing that you choose for u, but we typically try to choose u to be anything being raised to a power, any kind of higher powers of x, anything underneath a radical, or maybe something in the denominator or the exponent of e. So here I'm going to choose the denominator 5 plus e to the 3q to be u. So when I choose that, then my derivative du is going to be 3e to the 3q dq. So notice that e to the 3q dq is right there, except I need a 3. So I can't just stick a 3 there because that would change everything. So I need to stick also a 1/3 because 1/3 times 3 is 1. And you can multiply anything by 1 and it doesn't change. Now the 1/3 is the value I don't need, so I pulled that out. And so now on the bottom I have u, and on the top I have exactly du. So I end up with 1/3 the integral of du over u. This should look familiar to you. That's going to be the natural log of the absolute value of u plus c, carrying that 1/3. And then we plug back in what u is. Keep in mind, you can always take the derivative and make sure you get back what we started with. Now for I, this one's going to be a little tricky here because if I choose, like I said, generally with u substitution, you want to pick whatever's being raised to a power, anything that has a higher power of x, anything that's under the radical, whatever e is being raised to, or whatever's in the denominator or some form of the denominator. Now, it's not always going to work out exactly like that. It is trial and error, and you do need to practice. But if I choose this 5x plus 3 to be my u, when I take the derivative of that, I just get 5. And the problem is I've got this extra x right here. So what did I do? I chose u to be that 5x plus 3, as we talked about. And so then my du would be 5. However, if I were to solve this for 5x, I see that 5x is equal to u minus 3. So when I do my u substitution, that 5x plus 3 can still be u, but my 5x is now going to be that u minus 3. So now I have everything in terms of u. And I've got this 1/5 times 5 right here so that I can get this 5 dx to make it du, and I just pull out that 1/5 because I didn't need it. So now, the 4th root of u is u to the 1/4. I can distribute that u, and when I do, and I like bases being multiplied, you add their exponents. Now this is just simple sum and difference rule and power rule, and I can do u to the 5/4 plus 1 over 5/4 plus 1 minus 3u to the 1/4 plus 1 over 1/4 plus 1, carrying that 1/5 to everybody. And then once I simplify, dividing by a fraction is the same thing as multiplying by its reciprocal. And simplify everything, I'm now ready to plug back in what u is to get my integration, right? To get my antiderivative to this thing in here. So the trick was to notice that when you take this u being 5x plus 3, notice I've got this extra 5x right here. Well, 5x was equal to u minus 3. Rewriting this as a fraction exponent and distributing it. So I'm going to stop this video from here. Again, like I said in the previous video, I don't want to overwhelm you too much. And we'll do more practice problems in the next one. See you next time.